So, welcome back. In the last class, we were looking at partial derivatives and we had derived all of this in terms of Jacobians. So now, very briefly, Jacobians are defined in the following way, that I have two functions f of g, x of y, and this is the determinant del x f, del y f, del x g, and del y g, right? Where this is synonymous with del f, del x, y held constant, and del y f is synonymous with del f, del y, x held constant. It should be noted here that if I have del of f comma g, del of x comma y, now if I replace g by y, which I can do, then this is equivalent to del f, del x, y held constant, del y, x held constant, del x, del y, I'm sorry, this has to be del y, del x, y held constant, and this is going to be again del y, and this one has to be del f, del y, so that I am replacing g by y, and this determinant is, this is equal to 1, this is del f, del y, x held constant, and this is equal to 0, it's just del f, del x, y constant. So we are going to repeatedly use this relation that del of f comma y and del x comma y is equal to del f, del x, y held constant. So now we were looking at Maxwell's relation, and our original question was how many of them, how many independent relations do I have? So let's start again. So du, this is for a hydrostatic system we are looking at. So let's just write on top hydrostatic system. For a hydrostatic system, I have ds, TdS is du plus PdV, therefore du is TdS minus PdV plus mu dn. Always remember the first law, which is ds is du. For a hydrostatic system, it is du plus PdV minus mu dn, then you can manipulate this. And my Maxwell's relation read the following, that del T del V S and n held constant. This is because u is a state function and therefore is an exact differential, is minus del P del S V and n held constant. Then we had minus del P del N, S and V held constant was del mu del V, S and n held constant. Finally, we had del T del N, S and V are held constant is equal to del mu del S, V and n are held constant. So these are the three Maxwell's relations that we get from the internal energy. Once again, Very briefly, this is a consequence of the fact that u is a state function and therefore an exact differential. Right? Now I want to use my knowledge of Jacobians. Correct? So when we did Jacobians, we understood that del f comma g, del x comma y, we had this, and this relation, in this relation, if I substitute g is equal to y, then it follows that del fy del x comma y is equal to del f del x, y held constant. But here I have treated the function as a function of two variables. In principle, it can be a function of n variables, which means the generalization of this would be if f is a function of x1, x2, all the way up to xn, then del f del comma x2, x3, xn del of x1, x2, all the way up to xn is equivalently del f del x1, x2, x3 and xn being held fixed. So if you have learned partial derivatives by now, then you should be familiar with all of this terminology. Good. I want to apply this over here. So then let's look at the first equation. The first equation is this. And I want to write down the first equation in the following way. So del of t comma s comma n, del of v comma s comma n is equal to minus del of p comma v comma n as del of and del of s comma v comma n. So I see that the denominator here is vsn, on the other hand it is svn, but I can alter these two, and if I alter these two, then I should have del of t comma s comma n, del of s comma v comma n is equal to del of pvn del of svn, which means we had learned this when we in the earlier class. I can bring it on the left hand side to write it down as is equal to 1. Now remember, del of fg, del of xy, del of xy, del of fg is equal to, sorry, not this one. The result I want to use is del of xg, del of xy, del of xy, del of uv is equal to del of fg, del of uv. But this equation is particularly cast in this way. If you look at the left hand side and compare this part, you will see that it's exactly done in that way, and therefore I can write it down del of t of s comma n, del of p v n is equal to 1. Right? So this is my first Maxwell's relation. What about the second one? The second Maxwell's relation is minus del p del n s comma v is equal to del mu del v s comma n. Right? For the ease of it, I will simply write down this as minus del p del n. Since S is constant on both sides, I will simply write it down as del mu del V n comma S. And using this relation again, if I borrow it, then this implies that minus del of PVS del of NVS is equal to del mu of V comma N comma S and del of V comma N comma S. Again, you see that there is a change in, if I interchange N and V, I will absorb the minus sign here and I can write down this as PVS del of VNS is equal to del of mu NS del of VNS. This implies I will use the same argument that I have used before. Del of mu NS must be equal to 1. This is my second Maxwell's relation. What about the third? The third is del T del N S comma V. This is the relation between TDS term and mu dn term, right? You have del mu del S N comma V, so that you have del of TSV del of NSV is equal to del mu NV del of SNNV. So one possibility is that there is something, yeah, this is fine. Okay, so now NS, if I interchange, this becomes S N V, but I bring a minus sign in front of it, is equal to del mu N V del of S N V, and therefore I have minus del T S V del of mu N V is equal to 1. I can interchange mu and n here again, so that this becomes TSV del of n mu v is equal to 1. So this one is your third Maxwell's relation. Now, with all of this, did I make my life more complicated? Let's try to see. So now, as we said, we derived this Maxwell's relation stating u as an exact differential because u is a state function, and therefore we could arrive at all these three Maxwell's relations. The same argument is also valid for all the other free energies that we had defined. So remember, we had defined Helmholtz free energy F was u minus ds, and your differential df was du minus tds minus sdt. And if you now follow the first law which we had written down on top somewhere, yeah, exactly, du minus tds is minus pdv plus mu dn. So this becomes minus sdt minus pdv plus mu dn. This was the differential in the Helmholtz free energy. So let's apply. F is also an exact differential. It's a free energy. It's derived from u by simply replacing the entropy with its conjugate variable T. Now, so the first Maxwell relation would be del S del V, T and N held constant, is minus del P del T del P del t, v and n held constant. Then of course it follows minus del p del n, p with n and mu with v is equal to del mu del v. Here of course when you do del p del n, v and t are held constant. When you do del mu del v, n and t are held constant. And finally you have the last relation where you use s with n. So s with n and mu with t. So minus del s del n is equal to del mu del t. When you do del mu del t, your n and v are held constant. In this case, when you do del s del n, your t and v are held constant. So clearly now I can simplify my life a little bit. I remove the minus sign from the first. So if I now look at the first equation, what is the corresponding way of writing it down in terms of the Jacobian? Let's see. So this gives me del s t n, and I have del v t and n is equal to del p v n del t v n. Let's interchange v and t in the denominator over here and t and s in the denominator and in the numerator. So this means if I have del t s n, I will bring a minus sign which I'll use to do it like this, is del p v n del t v n. So effectively, in coming from here to here, what you have done here is del t s n. So del of s t n del of v t and n is equal to minus del of t s n, and I have del of t, v and n, which is equal to del of t comma s comma n, and I will interchange v and t in the denominator to write it as this was vtn. This itself was vtn, so I will write v, t and n, and I will write this as t, v and n. The minus sign is now absorbed in the denominator, in redefining the denominator. So therefore I have del of t, s and n and del of p, v and n is equal to 1. Let's see. Oops. Look at this. This equation is del of tsn, del of pvn equal to 1. So del of tsn, del of pvn. So this is not a new Maxwell's relation. We have already got this Maxwell's relation from the internal energy. So if you compare this and go all the way down, then we will see that we have the same equation that we had derived earlier. Both of them are consistent. Now what we want to do, so let me just see if I can zoom out so that you can now see that this equation and this equation are the same thing. Now let us zoom in so that we can have this. Yeah. Okay. Now let's look at the second Maxwell's relation, which is over here. We want to look at this one now. So this gives me minus del of PVT and del of NVT is equal to del of mu VT and del of VNT. So this is easy to do. I will just do one permutation in the denominator here to give you VNT is equal to del of mu Vt and del of Vnt, and this implies the Maxwell's relation in terms of the Jacobian is del of PVT del of mu Vt is equal to 1. Let's go up and see whether we have any of this. We have PVS, we have mu NS, we have TSV, we have N mu V, but we do not have PV, but this is something wrong here. Is this correct? Because there are two variables which are common. So V and T are both common in the numerator as well as in the denominator. So this is equivalently saying, so let's see where did we go wrong. Del P del N, V and T are held constant. You have del mu del V, N and T are held constant. So V and T. So then this is del mu del V, V and T, correct. So therefore this is actually V comma N comma T. I'm sorry. This is the part where it went wrong. So this is mu comma N comma T because I have mu and T, and this is V and T, and therefore this is not the right equation we are looking for. The right equation is del P, V and T and del of mu and T is equal to 1. And we go back to the other ones. We do not have a combination of PVT. Do we have a combination of PVT? We do not have. Therefore, this is a new Maxwell's relation that we have found out. This is new. Finally, the last one is del of STV del of NTV is equal to del of mu NV and del of TNV. There's a minus sign in front of it, which implies this becomes del of STV del of TNV. I absorb the minus sign by switching N and T here, is del of mu NV and del of TNV. And therefore the Maxwell's relation in terms of the Jacobian is del of mu NV is equal to 1. We do not have the combination STV. We have this here. So we already have TSV and NUV, and it is exactly this one. So this is again something which is not new. So from that Helmholtz free energy, we only get this as my new Maxwell's relation, right?